Hello, you're welcome back. Okay, so the topic before us is electromagnetic induction. Okay, now remember when we actually started with magnet, we get to understand that anytime there is current, anytime you have a conductor, either a straight wire or even a circular wire conductor carrying a current, okay, this particular conductor will definitely generate magnetic field around it. So there's always magnetic field due to um, a current carrying conductor, current flowing around the conductor. Okay. So now we are going to be looking at the opposite of that effect. All right. So now, which simply means that if this current actually changes, then the magnetic flux around this conductor will change. Now, this is the opposite of the effect. The opposite of this effect is what we have in electromagnetic induction. So, what is the definition of electromagnetic induction? Okay, electromagnetic induction is a process by which EMF is actually induced in a conductor. Okay, induced in a conductor by by varying the magnetic flux, by varying the magnetic okay magnetic flux linking the conductor, linking it. Okay, all right, to illustrate that, see a diagram here. This is the illustration. Here I have a conductor that's only connected to a measuring instrument, let's say galvanometer. Okay, this conductor wasn't connected. This is a coil of wire actually. Okay, wasn't actually connected to any source of voltage. The only thing that happens is that the conductor is not connected to any source, but rather connected to a current measuring instrument. Okay, so now I now bring okay a magnet, and this magnet is actually moved around this particular conductor. And of course, you know that when the magnet, every magnet will always carries magnetic flux around it. Okay, so by varying this magnet or moving the magnet around the conductor, the flux linking this particular conductor actually varies. So immediately you will discover that the galvanometer actually pointer reads, showing that current has flown through the conductor. So the question is, where does this voltage or this EMF come from? This EMF come from by a process known as electromagnetic induction. Okay, so invariably now, to actually probably simplify my definition or illustration, I'll simply say that electromagnetic induction is a process by which mechanical energy, okay, mechanical energy is actually converted to electrical energy. Yes, that is a very simple way of illustrating electromagnetic induction. Okay, a motion exists between a coil and, of course, a magnetic field, right? Coil of wire and a magnetic field. Motion exists, and what happened? Electrical energy is being generated in form of EMF. So please take note of that. All right. So now we're going to illustrate further. So now the person that actually studies in details electromagnetic induction is Michael Faraday. Okay, so then he now actually stated the laws of electromagnetic induction. So we're going to be looking at Faraday laws. Faraday laws of electromagnetic induction. Okay, so I hope you're with me. So I'm gonna state Faraday law. That's basically Faraday actually states basically two laws of electromagnetic induction, and I'm gonna be taking it one after the other. Okay, so the first law actually states that, of course, the first law is the actual definition of electromagnetic induction. Instead that whenever the flux, magnetic flux linking a conductor of current varies, then an EMF will be induced in that conductor. So mathematically, according to him, let me use E to represent EMF, all right? So um, whenever you have the flux, okay, of a conductor, this is change in flux, changes with time. That's how we express change. Change in flux with time, d flux the time, okay? Then EMF will be induced in that conductor. Now, since we are looking at in this case now, according to Faraday, Faraday actually studies this particular, or he conducted this experiment using a coil. Remember, a coil of wire is not just made up of just one, circle or one circular wire. We have many circular, okay, many turns. So invariably now that EMF now will, okay, the change is gonna be because is going to be multiplied by the number of tons, right? So we're dealing with number, not just one ton of conductor. We are looking at many tons of wire. Okay, a coil is made up of many tons. So according to Faraday, so this is actually this particular relationship is gotten from Faraday first law. So anytime there's a change in flux with respect to time, then EMF will be induced, okay, in that particular conductor. All right. Then there's one thing that Faraday actually introduced in his formula that I will explain later. That's going to be another law. That's a negative sign. Okay, which simply means that the EMF is always negative. It's always having a negative value to the change in flux. I will explain the reason for this negative sign. But let's look at the second law. Okay. Okay. So according to Faraday also, he said that this EMF is actually proportional, all right, to the rates of change in flux. The more the movement, the more the changes, okay, or the change in the linkage of this flux with the coil actually increases, you get more EMF. Okay, so that means the more mechanical energy you produce, either by varying the magnet, moving the magnet faster, you will have more EMF, or even moving the coil faster, okay, then you have more EMF. So that motion, the increase in that motion is proportional to the EMF that is actually induced. So please take note of that. So you can write that down somewhere, okay? So this is basically the two laws of Faraday. All right. So now let's now look at another law that explains why Faraday have to actually introduce minus sign to this formula, and that is called known as Lenz's law. Lenz's law. Okay. According to this law, okay, Lenz's law state that the induced EMF, okay, that induced EMF will always flow, always flow, always flow in a direction to oppose the motion that is actually producing it. Oppose the motion. Okay. So that is exactly why we can simply say that the EMF induced in a coil is always negative, okay, and multiplied by day. that change, by that change in flux, minus n multiplied by the change in flux. Okay, so the motion that is producing this EMF is actually this change in flux, and that EMF is always in opposite direction. So that simply means that if the EMS, if the change in flux is actually moving in the positive direction, then the EMF that is produced will move in the negative direction, vice versa. So the EMF produced is always produced and flow in a direction that is always opposes the change that actually that yields it. Okay, so please take note of that. Now, before we actually proceed, let's look at some basic formula which you already know. Okay, those formula are very important in solving question that have to do with electromagnetic induction. Already, we have already learned that magnetic flux density is giving us magnetic flux divided by area. So that simply means that invariably, I can simply say that magnetic flux is going to be equal to the magnetic flux density multiplied by area. So anytime there's a change, the change in magnetic flux can also be evaluated as, okay, it's got the change in magnetic flux. Of course, when there's a change, there's always initial and there's final. So change in magnetic flux is going to be the final flux minus the initial flux. And of course, the area will not change. What will change is going to be magnetic flux density. So in this case, now I'm going to have 4 flux to the final flux. That's going to be equal to B2, then, please pardon me, B2 multiplied by the area of the coil, then minus for flux 1, that's going to be B1 multiplied by the same area of the coil. So that way, I can actually conclude that invariably change in flux, okay, since area is common, that's going to be area bracket open. Area is a common factor, B2 minus B1. So put that in this formula, okay, in the formula of electromagnetic induction. So we can also write the EMF induced being equal to the number of turns multiplied by the change in flux with time. Okay, so the change in flux from here, we have A bracket open final flux density minus the initial flux density, then of course divided by change in time, and that's going to be T2 minus T1. Okay, so this and other formula, we are going to actually apply them. Okay, we are going to solve question because I'm interested in the application of this formula. So we're going to solve question, and that will be in the next video. Okay, see you in the next video. Thank you very much.